We move into our next session on the topic, Unleashing the Power of Quantum Computing. Quantum computing is a revolutionary new approach to computation that harnesses the principle of quantum mechanics to solve problems that are intractable for classical computers. Quantum computers are still in their early stages of development, but they hold the potential to revolutionize a wide range of industries, including medicine, materials, science, finance, and artificial intelligence. We have joining us virtually this morning Barry Sanders, Director, Institute for Quantum Science and Technology, University of Calgary. Barry C. Sanders is a physicist specializing in quantum information science, quantum computation, and quantum optics, and serves as, like I mentioned, the Distinguished Professor of the University of Calgary and as the Director of the Institute for Quantum Science and Technology. Ladies and gentlemen, he couldn't be here with us, so like I mentioned, he will be joining us virtually. Please extend a warm welcome to Barry C. Sanders.
Thank you very much for giving me the opportunity to speak about quantum computing, and welcome everyone to NASTech 2023. I'm looking forward to sharing with you the ideas of where quantum computing fits into business and what the implications are. To begin with, let me explain to you that there's a nexus, an intersection between quantum computing and data analytics. And in this slide, I convey to you what that intersection is. So first of all, data science is about capturing, maintaining, processing, analyzing, and communicating data, a lot of different aspects to it. Quantum computing, on the other hand, is focused on changing the very foundation of what computing is about. So normally computers we think of as operating with binary information, those are bits or zeros and ones, and executing Boolean logic. With quantum computing, we change the whole paradigm by replacing information by quantum information, and the entire logic has changed. So the implications of quantum computing are very deep and profound. It changes the whole game. The goal of combining quantum and data is to radically transform aspects of data science by exploiting potentially disruptive capabilities of quantum computing. The message is not that quantum computers change all of computing and all of data analytics, but only select parts. So part of the task ahead of us as we build quantum computers to scale is to figure out where quantum computers can give an advantage and where they don't. And quantum computers are fairly advanced today in a commercial sense. Quantum computers are available on the cloud commercially. Software frameworks exist so that non-experts in quantum are able to do programming and solve problems with quantum computers, and companies are investing in becoming quantum ready. This slide is meant to convey to you that data analytics, data science is quite broad. I mentioned before the capture, process, maintain, communicate, and analyze. You can see a bit.ly short URL so you can check out this information yourself. But the key point here is there are many aspects. You can see data mining, data reporting, regression, text mining, and so on. And we dive into all different aspects and figure out where the implications lie. So it's complicated, but very promising to study how quantum computing can transform all these different aspects. This slide is meant to convey to you the essence of what makes quantum computing different from today's computing. I'll often use just the capital letter Q to refer to the word quantum for short. And in the quantum field, we call everything that's not quantum classical. So you'll often see the term classical, it just means it's not quantum. On the left, you can see that information is represented by strings of zeros and ones. Boolean logic is used to process the information. A good example is the NAND gate. So an AND gate kind of multiplies the bits. NAND negates it, it just adds 1 modulo 2. And it turns out that the NAND gate is universal. So we can study how complex computing is by thinking of information and just dealing with the NAND gate. In the quantum computer, the information can exist in what we call superpositions. So it coexists in some way that just like waves can coexist and cross each other. We put the string of bits as inside of a funny set of brackets that we call a ket, and then we can superpose them. That's shown by the plus sign. And then we have quantum logic, and the quantum logic is able to process this coexistence of different informational states in a way that's intact, that doesn't just preserve the information, but preserves the relationship, the coherence between them. And then we have to detect. In computers, we take for granted that we can read things, but in quantum computing, we have to think about measurement. Measurement is a very subtle, challenging concept in quantum mechanics. So even the idea of measuring the result has to be handled very carefully. Whereas in a non-quantum computer, when the result comes out, we just assume we can read it. This slide is to convey to you part of the essence of quantum computing in the context of the famous Schrödinger's cat paradox. So in the early days of quantum mechanics, around 100 years ago, Erwin Schrödinger, Albert Einstein, and various others were perturbed by what quantum mechanics said. And Schrödinger said that if quantum mechanics is correct, then a nuclear decay doesn't happen. It's in a superposition of being decayed and not decayed. Two states coexist. And then he imagined that a nuclear decay triggers a poison gas that would kill a cat. And what happens is if the nucleus decays, then the cat dies. If not, the cat's alive. And they both coexist. So Schrödinger pointed out that an implication of quantum mechanics is that that even the notions of life and death no longer are separated, that we can imagine that something can even be in a superposition of alive and dead. So that's a big challenge to the way that we think. Nowadays, the paradox, well, the challenge to thinking still exists, but we don't just philosophize over it now, we exploit it. And so in the far right, that represents a quantum circuit where we send in zeros, but the zeros are in kets. They represent the quantum version of a zero. We send it through some gates. And here, 1 0 can be an undecayed nucleus. A 1 is decayed. 0 is live cat. 1 is a dead cat. And the output is a superposition of no decay and living cat with decay and dead cat. And so if we think of a quantum computer as simulating anything, it can simulate this paradox, and we actually use it. So the existence of this paradox is actually vital in being able to produce entanglement, which is a term that's often heard about in the public domain, and it arises out of this cat paradox. So quantum computers are real. They're being built with no fear or favor. I picked 3 different cases. The far left shows what I like to think of as the gold chandelier. It's a way of controlling a computer chip at the bottom of the chandelier. And the chandelier has different layers at different temperatures. And the idea is the quantum computer operates at a very cold temperature. In the middle is Xanadu's photonic quantum computer. And in the right, that's Honeywell's ion trap quantum computer. Various efforts are being made to realize quantum computers in different ways. We don't know which will be the winner. So right now, many different types of quantum computers are studied. And I wrote about this in a free-to-read booklet. You can see at the top, it says DOI. There's a website called doi.org, which is Digital Object Identifier. They provide a service to identify every published object by its label. And so if you want to see that free-to-read booklet, then to read about quantum computers, 10/CR58 typed into the DOI field will work. And you'll see these short DOIs later. I won't keep reminding you, but when you see 10/, if you want to look up the reference, go to doi.org. Now, the way quantum computing works is we just have a few, think of them as killer apps or valuable algorithms. And so this slide is meant to cover the 4 main ingredients of what quantum computing is about. On the upper left, this represents what's known as the Grover search. So Loeb Grover wrote a paper back in the 1990s, which essentially shows that an unstructured database can be searched quadratically faster. So the number of queries to a database to find a marked element is linear in the size of the database, but it's only square root if a quantum computer is being used. So we can do a quadratic speed up to searching unstructured data in principle. On the right, this is the famous Shor's algorithm, and this says that we get an almost exponential speed up in factorizing numbers. This is, and I'll talk more about it soon, but this has important cybersecurity implications. It's essentially a quantum computer can find hidden periods efficiently, and yet our whole e-commerce, our cryptosystems, our way of distributing keys RSA, if you've heard of that, or Pell's equation, or elliptic curve, or discrete logarithms can all be broken if finding periods can be done efficiently. Well, a quantum computer can do so. Lucky for us today, quantum computers aren't big enough, but it's a threat on the horizon. On the lower left, this indicates the effort to use quantum computers for optimization. There's no proof of advantage, but the idea is to find a minimum. The current meta-heuristic of simulated annealing uses an artificial temperature to get the computer to accept worse solutions, basically to climb up hills. But in quantum mechanics, we could get quantum tunneling and be able to go through barriers. So there's a lot of effort going on to look for advantages of using quantum computers for optimization, with some good results, but no rock-solid, rigorous proof. And on the lower right, and this is another 10/ or DOI reference, this is telling us about the variational algorithms. And variational algorithms are a hot topic at the moment. The idea is to take the quantum computer with some parameters, tune the parameters to try to find a lowest energy state, and this technique is being used by a lot of chemists. If we get serious about all these quantum algorithms, we can look them up. There's a website known as the Quantum Algorithm Zoo that's maintained by Stephen Jordan, who's at Microsoft Research. And the first algorithm is the one I mentioned to you, the Shor algorithm. And we can go through it, and this remarkably good website for referencing every algorithm out there and what the point is and what the references are. So as we get serious about exploiting quantum algorithms, there's a good site to look everything up. A hot topic these days is quantum machine learning. So there's a DOI reference, 10/GG73NF, written by Nathan Weeb, published in the New Journal of Physics, so it's a free-to-read article. This article 2 or 3 years ago says, what are the advantages of quantum machine learning? I'll have more to say about that in a moment. But first of all, one advantage would be quantum enhanced machine learning. So this is the idea that we do machine learning as we think about it today, but we speed it up by using quantum computers to do some of the inside steps. It can lower sample complexity, so it makes it quicker to obtain results by sampling different instances, a rich set of data models, and fewer computational steps, and so on. The other is to build a hardware device, so build some basic purpose-built quantum computer, and then use that as a machine and solve problems not with a computer, but with a purpose-built computer to do machine learning. So these are the different directions that go on, and quantum machine learning is a topic that is very hot at the moment, and so the idea is that quantum computers might help do better machine learning than without. Currently, the quantum computers exist in what we call the NISQ era. And NISQ stands for Noisy Intermediate Scale Quantum. Term is coined by John Preskill, Caltech. You can see the DOI reference to his article. And he says, now he was kind of the father of the group that promoted a lot of quantum error correction, which we need to get scale. And he said several years ago, he said, why don't we just put that aside and just build things and let them be noisy? You know, we don't have to make everything perfect at this point. And in his paper, he gives 9 reasons why it's a good idea to do a NISQ era. Most of us believe we're coming to the end of the era. So right now, the quantum computers of today have this, they're noisy machines. So the longer the computation, get exponentially more noise, which means it's harder. It takes much more sampling, well, exponentially more sampling to get the right answer. But he points out that we might discover something great. We'll get used to using quantum computers, and it takes us further to the post-NISQ era. And I'm mentioning this too because we're probably at the juncture where, and I know this with the companies, that they're now working on mitigating noise because we need to in order to push the power of quantum computing. Gartner is a consulting company that looks at the future, and this is 4 years ago. They wrote an article that was publicly available saying where quantum computing might fit in. And so here they say, given a certain number of qubits, what would be the application? And you can see that number 1 was chemistry, and that's certainly the case now that chemists are studying it. Optimization problems for hundreds to thousands of qubits. And we're in that regime. We have hundreds of qubits in some of the quantum computers. Machine learning and material science. And then if we get past 100,000 qubits, It's the unknown problems. So they're saying there are things that we probably haven't thought about that would become advantageous. So it's a few years old. It's a bit dated, this article, but it's still instructive to think about the pathway to applying quantum computers. Now, there's a program called the Creative Destruction Lab that started at the University of Toronto. It's now got over 20 branches around the world. It's a way of nurturing and accelerating startups. And one of the streams in that, based in Toronto, is the quantum stream. So a lot of quantum companies go through this Creative Destruction Lab stream. And Francesco Bova, Avi Goldfarb, and Roger Melko, who wrote this article, are the leaders, well, Avi's now moved on to another role, but they were the leaders of the quantum stream when they wrote this article. And it was really a study of commercial applications of quantum computing. So they wrote about the years of work with quantum startups, what succeeded, what didn't. And then in the shorter term, they point out that the real winning formula is combinatorial optimization. And they identified 3 key verticals. One is banking and finance, portfolio management. Another is materials and pharmaceuticals, to find the lowest energy molecular configuration, which is valuable for catalysis, say for the fossil fuels energy industry. It's also valuable for drug design and for various other applications. And another one is advanced manufacturing. The idea is to predict rare failures. So those are 3 highlights they picked as ways that quantum companies can move towards a profit. I'm just going to suggest a couple of examples here. So one is fintech, financial technology, and I've put in the DOI references so you can check what I wrote. One is an argument that financial processes, there's the Black-Scholes equation, which treats stock market like a diffusive process, and the equation is similar to the Schrödinger equation describing quantum mechanics in some ways. And so the idea is that, if finance can be described by the same mathematics that says how a quantum computer changes, then a quantum computer could offer advantages to modeling financial processes. Another application is, the shorter term is the optimization. So it's quantum enhanced optimization in the way that I showed you, that maybe we can tunnel to better optimal points rather than just use a temperature controlled way of leaping through them or other methods. Portfolio optimization is a good example of where optimization could help and quantum computers could lead to an advantage to find optimal trading trajectories and to leverage arbitrage opportunities. There's a couple of DOIs there, so you can look up those papers if you want to see the origin, and at least one of them led to a startup company specializing in this area. And then another is, this is the quantum machine learning. So the idea is use machine learning to identify patterns in financial data. And then if it's quantum enhanced machine learning, it could be even better at identifying patterns. So the quantum enhanced machine learning could help in using machine learning techniques for spotting those patterns, and then simulating the market behavior. So the quantum computer could allow simulations of the dynamics in the market better. 2 references given there. Another area of application is in health tech. And again, these, like the fintech, health tech, all of the stories are the same. Use quantum machine learning, use optimization, use variational methods. So I've given you the foundations of it, and now I'm just charting the path towards where it might be, where it might matter. And I've given references here too. Some of these references refer to IBM 2020. IBM wrote a report called Exploring Quantum Computing Use Cases for Healthcare. So that's 3 years ago. And that is a main reference in studying where health tech could benefit from quantum computing, but there's some other references here too. Support data-informed clinical decision-making, and using machine learning that's quantum enhanced to work through large, fast-growing data sets to assist with diagnostics. So diagnostics based on patient data. Another diagnostic is getting scans like MRI scans, CT scans and such, and then using quantum computers to help work through diagnostics for those. Another direction that's being explored for health tech is to improve precision medicine by enhancing, there's a typo, enhancing accuracy in risk predictions, the same as the enhanced risk prediction for advanced manufacturing. So same idea, different application. On the lowest left, you can see improved single-cell diagnostics to discover new biomarkers. As again, that's out of that IBM 2020 report, and the radiotherapy optimization on quantum computers. So radiotherapy is done, for example, for cancer treatment. Use quantum computers to optimize how much radiotherapy is done, minimize the risk, but maximize the benefit. And it also says the quantum-inspired algorithms. And so one thing, as I mentioned, quantum computers are not great at the moment, but we learn a lot by developing quantum computers. And so the quantum-inspired algorithms are those that arise out of studying ways to use quantum computers and then are adapted to non-quantum computers. I mentioned earlier that quantum computing is a threat to cybersecurity because it's very good at period finding. And the way that we do public key cryptography is in two steps. We distribute a key, and then we use the key to encrypt and decrypt messages. Quantum computers are a threat to key distribution because they're very good at finding periods, and the hardness of finding periods is what's meant to keep that first stage safe by existing techniques using RSA and similar. But the other side of using the key is also vulnerable to search attacks. I mentioned Grover search. So there exist ways to enhance the search, and then the consequence of that is we need larger key sizes than we thought. Quantum cryptography is the defense against quantum computing, but it's still not a mature technology. And so there's a big effort, notably in the United States with the National Institute for Standards and Technology, demanding that there be a standard to use non-quantum techniques to defend against quantum computers. So this is essentially an algorithmic research topic. How do we make use of quantum? How do we find problems that are hard for a quantum computer to break, but easy to check is really the task. And so that's going on, and we're hoping for a standard next year that could be used to defend against quantum computers. But we don't know for sure that even when they're approved, if they're really safe. So there's always a risk. And then the quantum cryptography approach provides information theoretic security, which means it can't be broken by any computer ever, but it's a physical implementation, so it has physical vulnerabilities, and also certain things like authenticating, so two parties have to authenticate. We don't have a quantum secure way of doing that, so there's all kinds of subtleties that have to be studied, but quantum cryptography seems to provide a viable pathway to keeping the world safe if a quantum computer reaches scale. Now, quantum computers won't just be machines you buy and put on your desk, but they'll be integrated into existing computer infrastructure, offered off the cloud, or be part of computer infrastructure. So you might make use of a supercomputer network to access time, and so we can imagine that quantum computers will be part of a supercomputer infrastructure that's offered over the cloud. There are three ways that I can see integration of quantum computers into the infrastructure taking place. One is just build regular computers, but we put in pieces or components or parts that are quantum, and then their access to speed up different sub-algorithms. So we'll probably have a point where we have computers. Quantum computer, though not the whole quantum computer is quantum, but parts of it will be quantum. Second is we'll interface them with high-performance computing, and for that, that's a workflow issue. So a problem is submitted to the machines, and then the work is partitioned. So some goes to the quantum chip and some goes to other parts. And so workflow management in the computer setting is key. And then the other aspect of integration is what I call chipifying. So right now we have, and you saw that picture with IBM and Xanadu and Honeywell machines, some are sitting on optical tables, all this. What we would really like to do is have them on tiny computer chips. And so over time, we hope to be able to move to chips, and then these chips can be incorporated with computers. Subtleties exist because the chips might have to operate at very cold temperatures, but if we can chipify our quantum computers, then we have a way of integrating the machines together. We have some problems, and that there's companies, efforts, a lot of investment going into quantum, but we're short of talent. And there's three problems identified here. So first of all, we're short of, four problems. First one is we're short of talent in everything. It's a rate limiting step to know what's going on in quantum. Then, when we do look at where we're addressing the skills gap, most of the training is going on in science, and yet the companies developing it really need engineers who understand the quantum relevant aspects. We also need the domain experts in finance, in healthcare and so on, well, health tech, fintech, health tech, and so on, to be able to understand how to uptake it. So the training effort in science doesn't address the entire skills gap. Another problem is that much of the training is at the graduate level, but not everybody goes on to graduate studies, and some training in the undergraduate level is needed to be able to prepare a workforce both to create and to adopt quantum technologies. And as we move towards quantum computers at scale, trades need to develop to be able to support. And I mean, an example would be optical fibers. Optical technology could be lasers, but we need people who are skilled to be able to handle all those kinds of tasks, those tasks. So that, I hope that explains to you my perspective on where quantum computing is at, where the opportunities lie. But this is a deep tech effort. The quantum computer potentially has great applications. There's also a lot of question marks. There's technical challenges, application challenges, competition with other technologies, and so on. So it's very exciting, very much worth an investment, very much important that we get ready for this and that we make use of the new algorithms and ways of thinking that come out of studying it, and watch this space. In the next few years, we could see a revolution if all the cards fall in our favor. Thank you very much.
That was Barry C. Sanders, Director, Institute for Quantum Science and Technology, joining us virtually. I'd like to thank him once again for being with us. We all just heard about how quantum computing